of the project that I did back during my PhD, which I finished in September. I'm starting here as a postdoc, as Ron mentioned, which will be these from initial conditions to protohalos and insights of their internal structure. But before going into there, I would just give a broad overview of why I've been carrying in cosmology and numerical simulations about these objects that I'm going to talk about, the dark matter halos. And afterwards, I'm going to give some comment about a very interesting work that I found recently that I think it can be very interesting to many people here, which is a broad concept that is coming now in machine learning, and it might be interesting even if you don't work in numerical cosmology. So, okay, let me start with this introduction. I think that all of the people here are very familiar with this, but if you cannot heard like this broad introduction. What are dark matter halos? Dark matter halos are gravitationally virialized objects that form, well, stable objects that correspond to high overdensities in our universe due to the gravitational collapse of dark matter. And we are interested in them because that's where galaxies form. And of course, that's what we observe when we conduct these galaxy surveys. And they are useful to understand as themselves because they serve as the building seeds where galaxies form, develop, and then we observe them. So how can we predict how these dark matter halos form and what are their properties? It's what I would focus on. So for introduction, from giving a very broad idea, but when one carries out one of these embodied simulations on liquid gravity, let's say, one starts with this very like Gaussian, or yeah, let's put it Gaussian initial conditions where everything is very well behaved. And you have slight small perturbations corresponding to like some inflation process that dealt these slightly differences in the overdensity. But as you run these embodied simulations where gravity kicks in, you depart from this very linearly perturbed structure to developing more and more complex structures, such as dark matter halos. You form other structures like filaments, like voids are there, pancakes, but what I would focus on this talk would be like the big super high density blobs that you see appearing here, which are dark matter halos. So basically the thing goes that you put in your simulation some initial condition that it's very Gaussian, like this Gaussian initial conditions, let's say. If not, you can also run a non-Gaussian initial condition, but the main idea is that through the evolution to gravity, you end up with these catalog populations of dark matter. So then one can ask, okay, so what's if I'm starting from, I'm going to take them the ruler, and if you start from these initial conditions, can you what are some recipes that can tell you where from in here would halos form? But another different question that you can also ask is that once that you look at the final populations of halos that are very non-linear objects, what are their properties? What's basically the degrees of freedom, let's say, that can characterize one of these objects? And that's very important because, as I mentioned, those features would be most likely the things that affect the galaxies that you observe. So both questions are very interesting, but not quite the same, although they are connected definitely. And that's what I'm going to talk. The first thing was a paper that I did with Marcos, Jens, and Raul Angulo, which was my supervisor, a PhD supervisor. And it's related to doing these predictions from initial conditions to the regions that will collapse into halos. And the second one, it's more related. So, and the technique that we employed here was based on a machine learning architecture. And this other work that I will talk about, it's about ones that you have galaxies that have formed in a cosmology at a certain redshift with whatever mass they have. What's their internal structure and what's setting this very important characteristic, which is the concentration of these dark matter halos. And that's an analytical work. It's a model that it just comprises a set of simulations and a physical notion of what's this mechanism. And I will talk about them separately. So let me start, I think, from the most natural project, which is the formation of halos or protohalos. And for that, I want to start with this very simple picture. Suppose that I provide you with the initial field of a simulation, and I ask you where halos would form. course, it is only a slice in 3D. The simulation actually is three-dimensional. But of course, if you only see these pictures and you see a slight over densities and under densities, you would think that, of course, the most overdense regions would collapse, the less like the more underdense regions would be voids, but it's not straightforward. Like if you see this image and then you just draw it, it's not trivial to see what are the regions that would collapse around. Of course, we have very nice analytical models that do predict this collapse, such as the scarcity theory or APS. And this is a work very interesting that Paulo here did also in collaboration with Rodrigo Vojvodic, which was taking this excursion set theory, which is a very nice analytical idea that it's based on smoothing the density fits at different scales. And from that, you can predict what within this initial field, what regions would collapse. So what I'm plotting here is just like an overplot. This is not the final halos. They don't look like these are the regions in the initial conditions from the other slides that would end up becoming a halo of a certain mass. Okay. So this is great. For sure you can understand what is going on here, because since it's a completely analytical model, you can interpret what are the things that are going there and how it's influenced. So you have a complete knowledge of what's going on. The con is that it's qualitative in some level. Like if you want to get very precisely something as the halo mass function and all these very fine-tuned dependencies, you don't get all these small scale, well, actually more detailed collapse features, let's say. Of course, then you can also do an embody, which is the resource that we have available nowadays that we think that is the most precise. And from that, then you run it, and these are actually different halos identified from that simulation. And you can all see that these are very complicated objects. Like actually, you can see some parts of halos that are like these red parts, which are part of the same halo, but they are kind of disconnected. That it's because like once that halo collapse, there's some involved material that might just be, this would be first infall, but then might go out, things like that. It's not trivial to interpret. And of course, even though it's very precise, it's the way in which we can do very accurate quantifications of this, they are very expensive to run. So what we propose here is an intermediate way of doing machine learning based on n-body simulations, but would allow you to have fast and accurate predictions of that. So those are actually the predictions of the network that we trained. But the idea here was that if now we want to do some like understand very complicated details of how these initial conditions determine the formation of halos, if you want to do that with n-body simulations, it's very expensive. Each time that you want to see how the simulation changed to some type of field, to some small change, you will need to rerun a simulation, and it's quite expensive. But once that you have trained one of these models, maybe you can also do like faster experiments checking those effects beyond just using them for being fast. Like if you are within the distribution, you want to do proto-halo catalogs, which are already by themselves pretty interesting. It's a great tool. Provides halo mass functions and also provides a way to measure Lagrangian bias parameters. So I'm going to talk a little bit how we did this. Yeah.
So the analytical models you mentioned, they provide an approximation to the halo's positions and masses.
So in this case would be what this thing is providing you at this stage. It's only the Lagrangian, it's in Lagrangian space. So it would provide what are the regions in the initial conditions that would collapse in halos of different masses. But you could try to affect that into Eulerian, doing some kind of perturbation approach or whatever recipe that you want. So intrinsically, EPS would do predictions in the initial condition space. But of course, then you can also embed this with other methods that somehow map these Lagrangian predictions to Eulerian. And then I think that actually you did that with some second order LPT, LPT. But yeah, intrinsically, I'm just in this work, at least I'm going only to speak about this initial condition space. I'm not going to talk about what would be the Eulerian positions.
This is hydrodynamic. I mean, what kind of model?
Embody, gravity only.
So like a collisionless loss of equation.
Yeah. So it's particles that interact gravitationally, and that's it. Why it's important? It's because it's true that if you include baryonic effects, these things might change slightly, but the major
No, but I just mean sort of many particles gravitationally, by Lagrangian, you basically mean a bunch of kinetic energies and a bunch of potential energies, and then you solve.
So yeah, so it's
Or you course grade somehow.
no. So okay, so you have tracer particles that are so you have an initial volume that you discretize in particle elements that would trace the density field somehow. Well, somehow you assign the to each particle the mass corresponding to the volume that it would be tracing, and you forward evolve it, and that's how what you are tracing with this is it's how the phase space if you would have it, but you're actually only solving like so there's two methods for tracing the full phase space. In here you do like only in real space, computing the force in each step and solving some well numerical solver for differential equations, some leapfrog or whatever you want.
But it's Newton's.
It's Newton's
Yeah.
on expanding background.
It's Newton's n particle, I mean, okay.
So
Yeah.
let me just clarify that a second,
Yeah.
because I think it's also very interesting because of people that might start doing simulations, because it's tricky. Suppose that you are in the CMB, and that's where you measure actually the field as such. You have things that do actually GR solving of the equation of states of different components. You can do that like with class, or like a Campbell, whatever, to redshift 0. And that would actually tell you what's the correct dependence of the power spectrum on the cosmology that you're treating. What then you do is you take this and take it back to a certain redshift in which you would initialize the simulation, but doing, let's say, linear or 2LBT, linear, some perturbation theory on Newton.
Okay,
And you have like a false power spectrum at that high redshift that would be that what you would use to initialize your Newtonian n-body simulation that you forward evolve. So the power spectrum here that you would put as initial conditions would actually be kind of false, because it's like, it's not what you would measure doing, like you do just with CAM2 or like with a CMB, with a GR solver to this redshift, but would be the thing that gives you the correct nonlinear behavior at the target redshift that you would be aiming, let's say redshift 0. Okay. There's other methods for doing this, by the way. Like this is one of the typical ways in which this is initialized. You can do other kinds of initializations or picking a specific gauge in which you can do it forward. Anyway, I lagged a lot. Now I need to go fast. It's my fault. It's not your sorry. So how we did this training on this machine learning approach? Suppose that I give you the initial density field, I can ask first the question of what would be the bosons, the particles in these initial conditions that would collapse into dark matter halos. That's one question. But the other is, once that you have the regions that would collapse, what regions would collapse into different halos? And that's another different problem, which is much more challenging because it's no longer a classification task. And I'm going to briefly explain what's the way in which one does it, because the classification is pretty straightforward, but this is tricky and I think interesting for other cases. Because what you are looking for in a classification task, if I say that I have in each image 100 halos, I would just need to put labels in between 0 and 100 and assign things. But here's not that like that, because first, you don't know what will be the number of halos that you would form in a different field of view. So the number of things can vary. And also their permutation in variables. It doesn't matter that I assign the number 1 to this halo and the number 2 to this other. You can see, just want to see what are the same things and what are the different things. No? So for doing that, there are different approaches, but the most mathematically elegant way, let's say, is this Weinberger loss, which is basically a loss that is doing the following. If I give you these regions that will collapse, I want to create an embedding, a mapping to a representation space, such that in this representation space, so they have the same dimension, this is important, and all the things that correspond to the same object here should be mapped closer together, but farther away from things that correspond to different objects. So what you have in the end, once that you train the network to do this kind of separation, would be a kind of clustered space in which you can identify different structures. So basically, it's a network that learns an abstract mapping where the things that belong to the same object clustered together. And funnily enough, when you look at this representation of space, they somehow give you a feeling of the cosmic web, even though they are not the same. Like this is just a representation that the network has learned. But of course, like things that belong to the same halos, they are closer, and then you have this continuous mapping. So that's the way in which we train this instance segmentation network, and might be applied to many other things. So just to show you some results, so you can visually check that everything seems to work fine. This is the results from the semantic network, if you are halo or not. So this is the ground truth of a slice. This will be the probabilistic predictions of each particle if it would be end up part of a dark matter halo or not. And this is like a residual map. But still, like you can see that to some reasonable level, the shapes are well captured. There's room for improvement in this because it's just the probability pixel by voxel by voxel of if you would be a halo or not, but it's not giving you a distribution. You could also think of terms of trying to learn a distribution of that, which might be important in some cases. For instance, these outer shells that are infolding, it's tricky because maybe some of them have like if if you change slightly the initial conditions would be like some chaotic effect, like slight changes in initial conditions would make you be part or not of a halo. So you can start to have like non-halos, multiple peak distribution or something like that. But for
So in this case, it's always like you have an initial time and a final time.
Yeah.
It's always like
you
don't have
in this experiment, I'm only training fixed cosmology, fixed redshift. We checked and I can show what it predicts at changing cosmology or redshift. We change sigma height in cosmology, so it's the same. It's learning features because I mean it's like this. In some cases, it would not extrapolate correctly. In other cases, that would be like differences in the background density, like with sigma height. It has learned it because it has learned to predict structure formation in regions with different mean density. But yeah, it's like that. And some results about the instance part. Oh no. So in here, I'm just showing true. I think it's going to shift back. Okay, well, true predictions. Okay, so you can visually see that not just the shape, but the predicted mass. So I'm coloring the things that belong to the same halo with the different mass that would correspond. They look roughly correct. But we need to quantify this a bit. I'm just going to show you a couple of things. For instance, the halo mass function. It is on my laptop. It's maybe it's an internet issue because it's okay. It's named it. So the halo mass function here, I'm just computing it for the actual things that we observed in the simulation with respect to the predictions of the neural network. And you can see that when you go to the very low masses, it breaks down. For the halos that have a that are very small, the network starts to fail. But then in a very good regime, meaning 3 orders of magnitude, it's working. And the nice thing is that since now the network is very fast and it's translationally invariant because it's a convolutional neural network, you can go to a very big, large box and do whatever predictions of the mass functions that you want because it's fast and you just need to put things together. Oh no! But this was a while ago when I did the. Maybe I put it on the. Maybe put it on the pen drive and use it on the laptop. Well, I would just pass when I start one thing. I would. Other things that you can do, you can actually compute the Lagrangian bias. How do you do it? You can just take different regions, change the background or like the mean over density on the background and see how it's the reaction of the network to that. That's not going outside of distribution because the network has learned a lot of patches with different backgrounds over densities. So if you check what's the response function of the halos that form with respect to the mean background over density that you are shifting, you can then from the derivatives of that function compute the bias. And here we actually show the blue line first. You can check the simulation measure with respect to the predictions. And you can see that they are very off by the Laceira's prediction, but that's only an effect of the box. They coincide perfectly. If you go to larger and larger boxes, which you can do because I have a very fast thing to evaluate, you can see as this converges towards the Laceira's measure. And finally, also, a funny thing that you can do, and this is very interesting for wind lensing studies, is that you can check the effect of that your field has with respect to tidal fields. You can just input different tidal fields to your initial conditions and check what's the response and how the shapes of protohalos are actually squeezed in one direction or another. It's the protohalos, just important. I'm not doing this for the final shapes, which is the actual relevant thing for your viewing, but if you have then a way to connect them, it's also an interesting thing to look at.
Good, sorry. Can you clarify a little bit then? What is the difference between a protohalo and a halo?
So when I say protohalo, I just mean by that, it's the region in the initial conditions that would be collapsed into halo at the target redshift. So it's I run the simulation, I identify all the particles in my redshift 0 that are parted up in a halo, and then I ask, what's the region in the initial conditions that these particles occupied?
Okay.
Those are the contours that they are representing. Okay, so good. I think that's a probe of something useful and interesting that one can do with machine learning and simulations. Now I'm going to talk a little bit about this other thing, which is interesting on another scale.
So before you move on there, so have you tested different properties in the initial conditions, or like
properties
like for example, let's suppose when they're not Gaussian distributed with maybe a change in amplitude in the initial conditions or a change of the slope of the distribution?
yes. So we didn't what I did not do because of the principles was going out of distribution, because it's a bit of the question of what do you want this network for. What we wanted to was to investigate.
Right, but I'm referring to distributions for the initial condition, right? In the distribution, you're assuming that is homogeneous Gaussian.
Yeah. So what the training that we did was fixed, so it was Plan 13 cosmology for the power spectrum. That's it. Different samples. We just changed for training again different samples of that power spectrum. We didn't vary. If we then try,
but you could, right?
we could do. I mean, you can execute definitely the network on that, but first, I won't guarantee that this would give you the correct results. And second, if it gives you the correct results, you might want to use that for interpreting something, but it won't be straightforward. Like what I'm saying is that this thing, if you give whatever distribution in the volume that it inputs, it will give you an output, definitely. Right. I can guarantee you that the results will be precise at a certain level within Plan 13 at redshift 0. And I could extend this retraining the network on different things. But the question is, if one has some specific thing that wants to be tested, it's great, because then it's like, now I want to build some, I don't know, emulator that is cosmology dependent. Then I would do
could you be able to see differences in the cosmology of the initial conditions?
Yes. So for instance,
different.
I'm not sure if, but we changed, for instance, sigma. We had, as we did here with the B1 or with the, we did sigma, fiducial sigmoid and two different sigmoids, which actually is pretty much corresponding to this, like changing the value density.
So it's a constant amplitude.
Yeah. So when you check, what you see is that the halos respond as you would expect, that if you increase sigmoid, the protohalos become systematically bigger, and actually that's correctly captured. So at that level, it works, and it's interesting. You could also measure some kind of bias, like response to sigmoid. Okay. So second project, very quickly, because I want to talk about the last thing, which I find very, very interesting. If you're interested not in predicting where halos would form, but what's their internal structure nowadays, we have some insights, and I'm going to explain one very interesting that we did in this project. So take the halos that form at redshift 0, then you can measure the density profile, and as people found out in 1997, you have a universal like profile that it seems to be invariant with respect to changes in cosmology. I mean, now our Conway did a very accurate job there. Still, there's some deviations, but they're like second order. Basically, the profile of dark matter halos follows roughly an NFW in a wide range. And why is that interesting? Well, because it basically captures what's the shape of the density profile across many, many things. And with that, you can do forecast for many things. You can, provide some kind of constraints on strong lensing. And I mean, the predictions, it's only going to tell you about how the internal structure of payloads changes with their certain things. But then that has immense consequences on different predictions. However, we found out that actually this was not very well studied about how a concentration model can predict changes if you change the cosmology, because this has been tested out when changing mass and changing redshift. But there was not that much of a heavy study doing changes in cosmology. So what we did was run a certain set of simulations in which all these different cosmological parameters were varied. So some are standard on the CDM, but we also included dynamical dark energy, W0, WA, and also a neutrino mass. And then from these simulations, we went there to this n-body and measured. And just focus on the points here, forget about the solid lines. What were those concentrations? And of course, you can see some changes as you would expect. No? Interestingly, when you change W0 or WA, which are dynamical dark energy, that's not affecting the redshift 0 power spectrum, or we didn't change it, we kept it fixed. But that changed the history of expansion. That's what the effect of these parameters has. And as you can see here, that definitely impacts the concentration that you are measuring, which is interesting, because that's straightforwardly telling you that not only the power spectrum is sufficient to determine to give accurate concentration predictions. It's also important on the expansion history that you have. And that links to a very neat idea that Anon had. I forgot exactly when, but I think it's 2016. That it's telling you the following: that the concentration of the dark matter halo at a certain redshift is actually fully determined by the history of accretion of how it formed, and not just the full thing, like not the whole history of accretion, but you can actually find a very interesting correlation as follows. You take a halo that has a certain mass at present time. You see the collapse mass history, which is just counting how it formed, like the mass that it was accreted in halos along the simulation. And you measure here a formation time. And you can measure it by saying when the halo assembled a certain percentage of its current mass, okay? And that gives you this point, no? So it's like, for halos that has this mass at redshift 0, they would have assembled half of their mass, for instance, at redshift 0.25 or whatever, and then gives you a formation time. And since you are in a cosmology, you would have that at that time, the universe would have a certain critical density. So you have a typical critical density at the formation time. Of course, we have also EPS, as I mentioned, as Carsten said, which is an analytical theory that can also allow you to predict the formation history, the collapse mass history for these halos, which is nice because now you can also have an analytical model for it. And empirically, then what we did was went to the simulations, all of them that we had, you saw that we ran a bunch of them with a lot of different cosmological parameters, and measure what's the relation in between their current density within the scale radius, like the thing that defines the concentration, and the critical density of the universe at their formation time. And that's from simulations. You see this very neat line that is actually, so it's varying all these cosmologies that depend with color, but you can also see points that go from redshift 0 to redshift 2, redshift 0 here, redshift 2 there. And masses in the range, I think it's from 10 to the, a little bit more than 10 to the 13 to 10 to the 15, okay? So it's very surprising that this kind of linear relation empirically holds for all these cases. It's cosmology invariant, redshift invariant, and also independent of mass. Okay, so with these things in hand, yeah.
Sorry, so this plot there, so again, this is just the critical density at the formation time. And then here is the density of that batch at that same time.
No, the enclosed density within Rx, which is the scale radius for at the redshift. Redshift. So it's basically telling you that if you know,
Yeah, okay, so,
you need to assume a profile. That's the thing.
yes, but,
Well,
if spherical collapse is,
forget about it.
no, no,
I
no,
mentioned it, but
yeah, so if I think about spherical collapse, it's not caring about what is the density, it's about the over density. This is a measure of over density,
right.
right?
So
So
wait,
it's like you're putting an anchor at some point in saying after that, it's when you're having collapse of that region. That's not
no,
correct.
I'm not explaining it
Okay.
clearly. So this plotting is only from, forget about any EPA, any excursion set thing. You just take the angles in the simulation, measure their critical density formation time and the density enclosed within RS, the scale radius, like the thing that defines concentration. You obtain this type correlation. Okay. That's actually just by itself pointing about this. So you don't need to think about EPS in any way until now. You're just saying that empirically you see that there's this correlation in between current concentration of halos with their formation time measured in simulations. But now I say, if this relation holds for all these regimes, I can then use EPS as follows. I now say, okay, I would like to know the concentration of a halo that lives in this cosmology and has this mass and this redshift. Then I use EPS to predict at that point what's its formation history, the dashed line. And if I have the formation history, I can actually determine what was the formation time. And using this empirical relation that I calibrated with my simulations, I can give you a prediction for the concentration. So basically what we will is a model that it's saying, telling me the concentration, telling me the redshift, telling me the mass, and I will give you a prediction of its concentration of that halo. And for that I'm using EPS, because I need to build a collapse mass history. I'm not going to run a simulation. I will just use the analytical EPS for the collapse mass history prediction. Yeah, I might not have explained it very clearly, but okay, just recapping. The simulations for us were useful for checking this relation that it just pops up, which is telling you this correlation in between carbon concentration and formation time exists, at least within this extended regime, which is covering a lot of regime. And the other thing is, since EPS, experiential theory, provides a way to compute collapse mass history, then we can build a model combining this calibrated relation with the EPS. So now we basically did the solid lines that now you can look at, which are the predictions of our model. I mean, this was calibrated. There are some like below 8% differences in the running, but like the important thing is that it's giving errors below 8% across all this wide regime, like 2 orders of magnitude in mass from redshift 0 to redshift 2, and in 8 different cosmological parameters, also beyond standard model. So this was yeah. So that's the last. Yeah. We use this for some practical applications in our group, this rescaling algorithm, which was at the moment a thing that we wanted to build for emulators. But this project was basically telling that, oh, it's very nice that now with just simulations and a very simple model as CPS, we can actually have a very powerful tool for predicting the internal structure of dry particles. So this is up to what I've been, well, some of the projects that I've been doing. I hope you like them, but I would like to finish. How much time do I have? Sorry, okay. About something that I just recently found out, and I thought this was very cool recently. Because I've been, I've mentioned a bit on the machine learning project that, this is very nice and such. But I mean, in the end, they are very big black boxes. And when you try to interpret what's going on, basically you cannot do one. Or it's very difficult to actually say why a network is behaving the way it's behaving. You can try to play around with certain things, but in general, they are very open. No. Recently, I just came out and I found some interesting work that I want to mention. So just to put a little bit of cosmological context and why we should care about this. So suppose that we have like these dimensions in which we can have accurate models, fast models, and interpretable models. If you are only one of these streams, it's pretty useless. But basically or roughly, we can imagine that our embody simulations currently are very accurate, of course, and they are interpretable. We know what we put there, but they are very nonlinear processes that it's difficult for us then to actually have a little bit more of a physical intuition of what might be going on there. Then we have the analytical models, such as for what I mentioned, the excursion set theory, and that's very fast. It's analytical. You can compute things very fast there, and it's interpretable because it's a great toy model for understanding lots of things. However, if you want to do quantitative predictions, it fails at some degree. No? And of course, machine learning is fast and accurate if you train it properly, of course, but it's a very black box. So ideally, it would be cool at least to have some kind of interpretable machine learning that would be compromising a little bit of these three things. Currently, we are not yet there, but these things that I saw a couple of months ago, I liked out. So this thing that I'm going to talk about are an anthropic paper that came up recently, and there was a very nice YouTube channel that explained it surprisingly well. I mean, if you understand Spanish, it won't harm you to look at it, but the anthropic papers are great. Like, they explain everything step by step, putting a lot of examples. They are really fun to read. So I'm going to summarize this a bit because there are very surprising results for how one can do interpretable things on machine learning frameworks. So, okay, one of the main lines of trying to go for interpretability in machine learning has been what is called this mechanistic interpretability, which is, as we do physics, we have a thing that we don't know how it behaves. The ideal thing to do would be to break it in smaller pieces, understand how they work, how they interact between each other, and then you have a kind of understanding of how the whole thing behaves. The problem is that in neural networks, typically the fundamental unit that you're based on this is the neuron. And the neuron is not a good thing for understanding because it can be, well, I mean, as you can see here, different neurons in different layers activate differently. And why? You don't know. So in the context of large language models, actually, they refer to this polysemantic thing, that it's that the same neuron actually activates with different inputs. But it's not the neural thing that actually it's the relevant thing. It's the whole state of the network. So one of the causes about this polysemantic activation that they mentioned is this superposition ansatz, which is what might be happening is that the neural network is actually representing independent features of the data in like some independent features encoded on the states of the network. Like it would be a top thing would be 2 to the n neurons, the number of features that the network will be able to encode. And so what they did in this kind of project by Anthropic was to somehow decompose a network that they trained in independent features using sparse autoencoders. And that's what I'm going to explain now.
So before you go on, the picture that you were showing before says having a state, not this one, the next one.
The next.
The actual ordering of the layers doesn't seem to be too critical for this. How do you put let's say there's a sequence, right? So one layer is on top of the other. So when you're talking about a state here, it's much more complex than the state that we are thinking about, because there's a certain hierarchy, starting with some layers and so on, right?
Yeah, but the idea is that we know that different input create different activation, which I'm going to call states of the network. Since we know, suppose that you work in a toy model, that some states are independent from another, one can say that they are independent on what they represent to us, but for the network, the linear independence might not be in activations of single neurons, but on the whole state of that network. So the idea would be to decompose whatever these activations are going on into a base that is independent. And that's what sparse autoencoders would be. That's the idea of sparse autoencoders. I'm going actually to explain this carefully now. So in the case of the large language models, I'm going to just focus on this because that's what their papers were doing, but then I will finalize connecting a bit with cosmology. What you do is basically you have for training strings like word, series of words, blah, blah, you train your completely black box of neural network. And if now you, to that trained network, you provide a new set of string, like is after the other, you will have a probability for each of the words in your dictionary. So it would provide like, this is the probability of the next state, whatever. Once that you have the neural trained, what you can do operational, and just keep stay with me here, is that, okay, now I'm going to just train another network, would be a sparse autoencoder. And this thing is just a network that takes as input the activations of your first network, maps it into itself, and in the middle it has a layer with a lot of neurons. So the idea is that it's not encoding the information that is there, it's actually separating it. So you have a middle representation layer with lots of degrees of freedom, and you are going to impose in this intermediate layer some kind of independency of the states. So the idea, the idea of this is that this is part of the encoder, but what you are going to ask it is to do a mapping of the states of your network, which you cannot interpret, in the activations of some latent intermediate neuron layer in which the activations would be independent. So this is going to learn independent, how the states map into the independent context, contents of what you are putting there. And just for actually making an example of what these do, I need to give, now that I'm here, I need to give some publicity to Paulo and such. Suppose that now you give that you've trained your autoencoder, and now you provide these different things and see the activations. So when you do the mapping, you obtain the following. When you take the activations of the neurons here, they would be a lot. I mean, this is not going to be two-dimensional, but it would be some kind of clustering. So if I go and follow where the Isle of Sao Paulo would go, we'll go into a region of this latent space. If I now find the Isle of Sao Paulo in Portuguese, it would also be mapped to the same regional space, because the network actually has to learn also not just like it's invariant to it's learning concepts. It's not dependent on language, which it's very important. But then if I go to Lopez-Cano, maybe it would be mapped closely, because USP would be related to the context of Sao Paulo, but it would be a little bit farther away, and maybe it would be still within a certain cluster of universities, because universities would be also a kind of similar concept there. And well, the following are kind of similar, just that more different concepts would be mapped farther apart. And also, funnily enough, you can also, it's not just multilingual, it's multimodal. They try to put images there, and you can also play around. Like the concept of like green grass, it would be associated with green. So it's cool. The important thing is that in here you have a latent space that you can interpret directly, because if you go to a region and pick up some word, you will see that around that word there's also the mappings of similar words like that. And that's something that you can start to do for interpretability. And just now I will show you the results that they show in the network. Some of them are pretty funny. So for instance, in here they were putting things of the Golden Bridge and things and concepts related to that. And you can see that in some regions of this space, there's the concept of San Francisco. Farther away is the things related to earthquake and such. But more importantly, if you go to the text, you can see how the latent space, when you focus on a neuron that is associated with the tree ring of San Francisco, when something related to I didn't put the San Francisco. Well, okay, so the transit structure, if you go to the neuron that is fired with the concept, some kind of transit structure, it's activated with bridge, with underwater, with bridges, aqueduct, blah, blah, blah. So that latent neuron is associated with the activation with respect to that. And you can do also with other things like here, which are fine, but they try with many things. And you can turn this around. So since you know that the latent neuron that fires with a concept is this neuron in the latent space, you know now that what's the configuration of your large language model that it's fired with that. So now you take the neurons that are highly activated by let's say the Golden Gate Bridge, and tune their activations high up. And now you have a new large language model that it's triggered like a maniac with the golden bridge. So you ask, so this is the normal answer, no? What is your physical form? I don't actually have a physical form. I'm an artificial intelligence, blah, 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 blah. If you now take the golden bridge network that has the activations higher up, it says, I am the golden gate bridge, a famous suspension. So it's obsessed with this. And also you can do it with more interesting things, such as you have the neuron associated with bugs in code, and you put it down and you have a network that basically gives you code with very little bugs. Or you can do it the other way around and have a very completely useless but funny ways of taking out of, like me, or coding. And I mean, you can, they actually, the way in which they wanted this for was for steerability. That's what they call it. So for instance, that the network does not tell you how to build a bomb or something like that. You just put those things down. So it's not talking about bombs out or whatever. For our case, I don't think this is that interesting, but I do think that we can translate this exact same kind of architecture to, instead of being a large language model, we just put now kind of cosmological information. You have like the, let's say the advection, like the Lagrangian displacements of a simulation at a certain time, and you want now the probabilities of that displacements at a certain other different time, no? And you would have this kind of probabilistic mapping, and if you go to this next representation, you could maybe start to see features that correspond to physical states of things, like when a halo it's relaxed or unrelaxed, when like interpretability features, all these things. So this is, of course, I mean, it's not a particular idea of a concept that I have, but I just wanted to bring this up because it's a thing that came up recently, and for me, that I'm very skeptical about a lot of interpretability and explainability in machine learning models. I think that this is one of the few things that I've seen that might make more sense. It won't tell you what's the physics going on, but might be a good tool for having things that are disentangled in many different contexts that you can play around and actually find out what's the physical meaning of different features. So I just wanted to share this with you, just in case you find that interesting for your work. That's it, and thank you all for attending.
I mean, all your plots with the history were about the overdensity, right?
So in the protohalos.
Yeah.
So yes, it's the initial the input for the n-body. Yeah. And
Is there any information about velocities of this?
so actually I put the overdensities, we train on the potential actually,
Oh, okay.
which is containing, so the thing is that, but if I give you the full box of an n-body simulation, the density P of the full box of an n-body simulation, that contains all the information, because the velocities are computed into one LPT or two LPT for that case. So all the information is there. It would be redundant if I would provide the positions and velocities in the initial conditions.
Okay.
It's not missing, I'm not restraining information, like the input that I'm putting there, it's all that is, or the problem is determined. Yeah.
Well, wait, I mean, in principle, not really, because you have if you think about this thing as some kind of gas, you have a velocity distribution.
Here it's called dark matter. It's like, you know, like we are not, if it would be warm dark matter, that you would have some phase space and velocity distribution. Yes.
So it's dust.
It's called dark matter. Yeah.
This
Yeah.
is the energy momentum tensor is a dust.
Yes.
Okay.
So, on the interpretability, this is still there, so go back next slide where you have the intermediate,
The latent.
yeah, I just wanna see if I can figure. Yeah, it's one there. So is this, you have to make some choices for how much of the latent how large is your latent space, right? It's,
Each stage is great. Because it's the plot that I showed. They trained different like networks with different sizes for the latent space.
right.
The larger, the more concrete concept each neuron understands. The smaller, the more abstract and general concepts
Yeah.
it
Right.
learns. So in here you can see that there are like points of like blue, green, and I don't know, beige.
Yes.
They have increasing number of features, so it gets overly specialized.
Yeah.
So maybe one learns like these traffic infrastructures, but then the one with more features learns bridge, tunnel, road.
Right. So, yeah, so the way that I see this is like, sometimes we have these, the very simple, crude way that we've been doing something like this is through feature importance, you just delete something and see what the effect is.
Yeah.
This is like a supercharged, super tunable way of testing this,
And
right?
expensive.
Because-
So
Yeah. But I mean, if you have a very large latent space, then you have to map that with many different drivers. You don't know in principle where you're going to end up there, right? I mean,
there's
you have
no,
to, when you make a plot like this,
yeah,
you have used many instances there to map out what it is in latent space.
Yeah.
So if it is very high dimensional, then interpretability becomes a problem because you cannot possibly map that high dimension. However, so there's a middle ground there. So the thing is that you can increase the latent dimensionality of this space. So you start with a low dimension, you get the abstract feeling, and then you start to.
yes and no, because
No.
yes, I mean, the only problem, maybe there's a way to do like that, but if suppose that you first train only like a network with less features and then another with large features, you don't have any guarantee that the region in this latent
Yes.
space that it's mapped would be,
Right.
maybe you can actually use, I think you can do something like that. Like you train the network, you have some weights for the small dimensionality. And you now duplicate the number of neurons, but initialize the training with the weights from the other previous one. So you can maybe, I mean, I don't know, I'm just speculating
Yeah.
completely, I don't
You
know.
can prime the system.
Yeah.
You start with the weights of the, let's say, lower dimensional.
Might be a way.
Anyway, but yeah, I guess, I get you, I get the idea.
The funny thing that I actually find here is that most of the works that I've seen in interpretability, also in cosmology, the way in which latents or representation space are used, it generally is for compressing information. It's like autoencoder wise, because it's like what is the number of independent variables in my system, putting some kind of laws that also makes this thing independent. It's cool that people are the versions or whatever. But in here, it's a bit the other way around. Like we split in all the independent features by creating a lot of different representations that might map to different concepts. So it's related, and somehow it's the other way around. But I mean, it's fine, no? Because one question is what's the number of independent variables that would be affecting the system, and the other is what are the different features related to what I've learned, which in the context of cosmological simulations, it's more abstract, I would say, because in language we have concepts. What are the concepts in here?
We'll hear from you in a year.
I don't know.
Maybe you will.
I don't know, maybe I would.
Before.
I mean, yeah, I mean, well, whoever does something on this, I would like to hear this applied to physics, because for now, maybe they've done, there has been some advance, because I think this is 3 months old or something like that. But I've only seen this applied to large language models, which they're super cool. I mean, I'm super excited about this. But for physics, I would like it even better. So it's true that still would be interpretability. You need to go by hand into this latent space and figure out what is going on there. It's not going to give you things for free. Physicists are still required, which is good for us. But I don't know.
All right. Anything else? No?
So, yeah, sorry, just to be clear, all of these filaments, this is all dark matter. Visible matter has no paper in this. Like visible, all these filaments, this is dark matter.
No, wait, what?
Yeah.
What do you,
It's
like,
not even physics.
yeah.
No, I mean, no, this I know, but the filaments that you were showing before,
Here.
yeah, these things. Yeah, this stuff is dark matter.
Yeah,
This is
only
not,
dark matter.
this is with no.
All dark matter.
Okay, I see, fair enough.
So, yeah, there are also like simulations. Yes, Stuka has this very nice package for doing with warm dark matter. I mean, I don't, also there's for hot dark matter, but I don't know about that because they do both Einstein simulations. They solve the Schrodinger Boson equation. I don't know what, but I mean, the thing is that in the, you can have this for a velocity distribution for warm dark matter models also, and you need to trace the full phase space distribution. But in here, you just suppose that there's no velocity dispersion, which is what we believe most are. Like, I'm sorry,
No, it's
dark
okay.
matter, but
No, I'm just trying to,
the rotation curves are dark matter. At least this is the way in which typically embodied gravity of the simulations are one, most of them.
I just will talk, yeah, I have few, I would like to understand sort of the physics of these relations. So,
Okay, great.
you
Okay,
Okay, everybody, thank you so much. Thank you.
And I think we come back in March. Because now it's December, then we have the big meeting in at the IFT, then January and February, no one's gonna be here anyway. So we will come in March. So that's it.
always